We're excited here. This is the first seminar talk in our ongoing series here that's going to occur for the Center for Quantum Networks. Just introduce myself. I'm Russell Ballier. I'm the Assistant Director of Engineering Workforce Development for the Center. And like I said, the series, the hope is that our first few talks are going to give everybody kind of a broad overview of quantum information science and engineering or technology. And then we'll start to get into more technical talks as this series goes along. So our first speaker today is Dr. Michael Raymer. He is a Knight Professor of Liberal Arts and Sciences Emeritus at the University of Oregon, and he is a senior personnel for the center. He was the founding director of the Oregon Center for Optical, Molecular, and Quantum Science, and his research is in the area of quantum nonlinear optics. And in the 90s, his group pioneered the field of quantum state tomography. And I believe he's going to talk a little bit about this, but his effort, along with Chris Monroe's, to lobby the US government to support research in quantum information science and technology as a national priority, culminated in the passage of the National Quantum Initiative Act in December of 2018. So, and on a more personal note, I want to mention that Mike has been a great help to the engineering workforce development team with his ideas, and his willing to participate in these types of things like this seminar. So with that, I'm going to hand it over to Dr. Raymer and let him get started.
Thank you very much. Okay, so I'm still seeing Russell there on the in the thumbnail photos, but that's okay. I'll just turn those off. Okay, let me know if you have any problems seeing the slides or me speaking or whatever. So welcome everybody. It's a great pleasure for me to present this overview talk to kick off the series of the seminars for the Center for Quantum Networks. People ask me what this talk is, and I give it, my joking answer is that this particular talk is quantum information science for lawyers. And so the idea is that our center puts a large emphasis on studying the social impacts of technology, and in particular, quantum information technology. And so, this area has very large policy and security implications. And if successful over the next 20 or 30 years, it will change the way the internet works and will change many different technical kind of products and activities, just like the current internet changed everything, for better and for worse. So we have to keep track of what the potential downsides and threats are, as well as the fantastic new things we can do with this new technology. So I will give an overview of quantum information science and technology, and then I will follow that with a separate section, a kind of a physics introduction for beginners about quantum physics and quantum networks. So as Russ mentioned, Chris Monroe, professor at the University of Maryland and now at Duke University, and I, a few years ago, began a lobbying effort to the US Congress, and it involved many academics and industry scientists. And we ultimately were able to have the Congress pass this law or bill called the National Quantum Initiative Act. It was passed in the final months of, actually the final days of 2018. And since then, it's been funded at quite a high level, hundreds of millions of dollars per year, and this will be ongoing into the future. And this act has generated lots of new opportunities for scientists and engineers and educators to partner and team up together and work together across the entire continent for the national good and to advance science in new ways that were not possible 5 or 10 years ago. So what is quantum information science? Well, historically, we, at least with hindsight, we now look back on the early days of quantum technology. We call that quantum 1.0. And this refers to harnessing quantum physics in somewhat of a more familiar context, at least familiar to physicists and engineers. And this has led to technologies such as the computer, lasers, atomic clocks, magnetic resonance imaging technologies, and so on. All of these technologies do rely on quantum physics at their root, but they don't typically deal with individual fundamental particles like electrons or single photons of light. So now we're entering a new phase called Quantum 2.0. And this refers to harnessing quantum physics in the regime of a few particles, one, two, or a few degrees of freedom, which means basically the ways in which these particles can move or behave. So we isolate the behavior of these particles to a very high degree. And then we introduce what's called large-scale superposition and entanglement. And in this talk, I will describe those in great detail. It is the superposition and the entanglement that really distinguishes these technologies from the quantum 1.0. And I'll talk about what we can do with those. So I won't talk about the politics and how Chris Monroe and I were able to lobby Congress. That's an ongoing process. We're still lobbying many different congressional offices to advance the funding. But what I will do is I'll give you the pitch that we presented to the congressional staffers and some Congress members themselves about what this new technology can do if it's successful. So we break it up into three different pillars: quantum computing, quantum sensing, and quantum communication. And of course, the CQN, which this talk is being sponsored by, is a center to study quantum communication. Now, all of these technologies involve new capabilities that really could not be possible using the conventional approaches. So I'll go through these quickly one by one. First, let's discuss quantum sensing. Well, a sensor is just something like a temperature sensor, like or a gas sensor that can detect a certain change in the environment. So we'd like to measure magnetic fields. How strong is that magnetic field as you fly across different parts of say the North Pole, or if you're walking near a hospital and there's an MRI machine in there, how strong is that magnetic field? Or inside of biological materials, like inside of a single cell, there are actually magnetic fields, and you can probe perhaps inside of cells to measure these fields with increased precision and accuracy. Similarly, we have gravitational fields. If only I could spell gravitational, that would be nice. I see there's a mistake. But if you can measure the strength of gravity as you move around in some geological area, you can actually map out the density of mass underground. So, things like oil and sand have a different mass density than things like lead and gold. And you can actually map out different structures, different mineral deposits, and so on underground using a quantum mechanical gravity sensor. Materials engineering is a very big part of quantum science, and sensing plays a large role there, such as measuring the material properties at the microscopic level. GPS-free navigation. If you're in some environment, such as deep under the ocean or under a mine, underground in a mine, where there is no GPS access, how do you navigate? It turns out if you have a quantum technology-based gyroscope, if it's good enough, you can actually just use the gyroscope to navigate directly. And this is currently not possible with any precision using classical techniques. And finally, distributed sensing just means if you have many distributed sensors, namely sensors that are spread over some large area, you can kind of team them together and you can outperform any single sensor. Well, we'll just show a couple of examples. Here's a photo of a laboratory setup at Stanford University. It's called an atomic accelerometer. It's a large pipe. It's a few meters tall. And at the bottom, I've animated a blue ball, which is a cloud of atoms, maybe 1 million atoms. And you shoot from the bottom up with a laser pulse, and you accelerate those atoms, just like hitting a ping pong ball with a paddle. It goes up and it comes down. And it actually goes up and accelerates down at the same acceleration and the same velocity as a ping pong ball. So here it goes, boom. And by measuring very precisely using lasers and quantum techniques of the accelerations of that ball of atoms, you can measure the strength of gravity locally, very precisely. So if you move this sensor around in space over the ground, you can map out the density of ground mass underneath. Okay, another example, telescopes. So you might have seen recently some nice images, actually the very first images of a black hole, which looked sort of like a donut, which sort of made me hungry when I was having coffee. But the way they imaged this black hole was actually by combining the signals from, I think, about 10 or 20 radio telescopes that were distributed around the entire Earth. And they were able to record these radio signals electronically and put them on a hard disk, and then bring all those hard disks together and into a computer and process all that data together. So that's called a distributed telescope. Now, it turns out in the optical regime, which is what we see with our own two eyes, it's more difficult to do that because the wavelength of optical light is much shorter, smaller than the wavelength of radio waves. So there have been many experiments carried out using optical distributed telescopes, but there are proposals now for improving the sensitivity of such optical telescopes using quantum entanglement. And I'm actually working on a project with the University of Illinois in that direction. Finally, I'll mention biochemical sensing. So here we have a typical protein molecule that has important biological importance. And chemists really learn a lot about molecules and processes by measuring spectroscopy. Namely, you put light in to a sample, you see what light comes out, you measure the different colors, and you learn a lot about the structure. So we're also working on quantum mechanical techniques for enhancing molecular spectroscopy. So those are all examples of sensing. Now, moving along quickly here, let's talk about quantum computing. Well, I have a list here of the kinds of applications that an ideal quantum computer could solve or provide best answers to far more quickly and efficiently than any classical computer ever could do so. For example, optimizing various complex systems. I'll give an example later. Designer molecules. If you want to design a molecule, you have to solve the equations of quantum mechanics that describe the structure of the atoms and the electrons inside that molecule. It turns out that's too difficult to do for any supercomputer that now exists. However, an ideal quantum computer, because it works directly with the quantum principles itself, it can simulate the quantum principles and the quantum structure of a molecule. And this ultimately can be used to design new materials like solar cells, new pharmaceutical drugs, and so on. Pattern recognition. If you have massive amounts of data recorded about traffic, for example, could be cars, it could be airplanes, whatever. Could be more complicated things. It could be traffic patterns of information on the internet. You can use a quantum computer to work out the patterns that are happening. Machine learning and artificial intelligence are other applications that people are looking at. And finally, decryption of certain kind of encrypted messages could be carried out more efficiently using a quantum computer. And when I say more efficiently, I don't just mean 5 or 10 times faster. I mean in a sense that a classical conventional computer could never solve these problems in, say, 1 million years of processing. Whereas a quantum computer, if it's really built properly, could solve it, within 1 day or so. So it's really a huge difference. A nice example of a quantum computer is shown in this slide. This is called a trapped ion quantum computer, and the metallic blades there are a few centimeters in length. And then at the center, between 4 of these blades, there are 50 atoms trapped with fields, magnetic and electronic fields. And these 50 atoms are all lined up in a row, and you have a photograph of those atoms. If you shine laser light onto those atoms, each one glows, and emits light that can be imaged on a camera. Now, within each atom, there are, of course, electrons. And at the bottom, I've shown a little cartoon of a spinning top. This is a very nice top that you can actually buy online, and I just stole the picture from that. It's a very nice top that spins for a long time. But it's meant to represent that an electron can spin counterclockwise or clockwise relative to some axis, which I've drawn here in the vertical direction. And that is how quantum information is stored in that particular electron in that particular atom. If it's spinning counterclockwise, it could be called a 0. If it's spinning clockwise, it could be called a 1. And those are the binary or digital, numbers that information are recorded in. So if I have 50 atoms all trapped there, and each one can be in one of two states, if I just take 2 to the power 50, I get this huge number shown in green. And that's the number of different combinations that these 50 atoms could be in with regard to their state. These are different combinations. Now, classically, you could write down, 1 0 0 0 1 1 0 1 1 0 0 0 all the way up for 50 of these, and you could write down a list of zeros and ones, and that would be a particular one of those, trillions of states. However, a classical computer can represent only one of those states at a given time in a given set of 50 bits. But a quantum computer, because of superposition, which I'll describe later, can actually represent all of these states simultaneously, all at the same time. And this is kind of a parallelism of data storage that's not possible in a classical computer. And this is one of the key points why a quantum computer can be faster, more efficient than classical computers. So in order to compute a mathematical problem, or a solution to a problem, you have to carry out what are called gate operations. And conventional computers have gate operations that, like an add, you add these two numbers together, you spit out the answer. In a quantum computer with trapped ions, you use laser beams. You focus one laser beam on each of two atoms, and you have other fields like microwave fields, and you can manipulate the states of these so they exchange information, and they process a bit and process two bits and yield a calculational result in the form of 2 bits. So basically, it's kind of almost like dancers are interacting with each other and producing a result depending on how they interact. So if you do this, many times in sequence, you can carry out a calculation, and this is how a trapped ion computer would work. One of the companies that has been leading this area of trapped ions is called IonQ, founded by Chris Monroe and Jungsang Kim. And just by the way, this company recently went public, and they were the first quantum computing company to sell stock on the public exchange. So interesting story about this is that each one of these little metal blade traps can store about 50 ions. And for technical reasons, you cannot store more than 50 ions in a trap and still have it be useful. Basically, you can't access each ion with the laser beams properly if there's too many ions in the trap. So what you do is you build many traps. Here I show 4 traps. And then you do calculations or gate operations within each trap, but then you have to somehow have these different ions traps communicate with each other. So you can think of these as like a 4-core processor. Many laptops have 4 cores or 5 cores or 6 cores. Each one of these traps is like a core, but the cores have to talk to each other. So how do you do that? What you do is you hit one of the ions with a laser pulse and you make it emit a photon, which is shown as the green wiggly line going to the right. Those photons travel into this large blue box where there are mirrors and photodetectors and other operations which cause these photons to interact. And when the photons interact in the blue box, that kind of transmits backwards an interaction or entanglement into the traps. So this is a subtle point, but I'm going to skip over the details there. The point is that from the point of view of an optical scientist, such as myself, the challenges of building what's inside the blue box for a quantum computer is very similar to what challenges are present when building an optical network. You use low loss optical fibers. You need to have good coupling between the fibers. You need to have good detectors. You need to build error correction. You need to have good control lasers. All of these things are similar to the current internet, but in this case on a smaller scale. Now, going forward, of course, the CQN is going to try to be scaling up networks from outside of the lab, from inside a lab, and on a single campus, then across many campuses. So this idea of optical networks connecting different quantum units is essential not only to large networks like the internet, but also, as I show in this picture here, building a modular quantum computer with different core elements in it. Okay, so one example of what a quantum computer can do, I mentioned several already, but this optimization problem, for example, minimizing some cost function over a combinatorial large set of possible solutions. Well, this is a mathematical statement. Let me just show a kind of a cartoon of an idea, designing a robust energy grid. And you see in Texas, there are many of those. And we know a few months ago, Texas had a real problem with their energy grid becoming damaged and unstable. Now, I just saw a message that my internet connection is unstable. So if I freeze up, somebody jump in, let me know that. So the idea is that you would use a quantum computer to have the computer consider many different configurations for how to make these different interconnections in the most optimal way, such that if one or two of these lines failed, you want the grid to be more robust and be able to route the power around those failed links without having a catastrophic breakdown of the whole system. Okay, that's just an example. We get finally to quantum communication, which I think is the main interest here. Well, there's always a problem with security, and there are techniques for making information transfer more secure using quantum techniques across an optical fiber network. The other point called remote quantum computing is that if you have 2 or 3 computers that are functioning well at the quantum level, but they're separated by many kilometers, and you want to access all 3 of those from your location, you can do a couple of things. You could just send the problem to the computer and have it come back in the form of the answer, in an ordinary computer like your laptop. But more ideally, what you would like to do is formulate the problem in a quantum mechanical context on your computer or in your trapped ions, your quantum computer, transmit that quantum information to a remote quantum computer, have that remote quantum computer process the data and provide some kind of a solution or an answer, and transmit the answer back to your trapped ions in the form of quantum information, not in the form of classical conventional bits. This is a very, very hard challenge, which the center is working on. So let us now talk a little bit more specifically about quantum internet. This is an image that was created for the Center for Quantum Networks, and we like to show it often. It shows, the white lines here are the main trunk lines of a quantum network across the continent, and we have users, and it's shown as a little cell phone here on the right-hand side, hanging off of there. We have quantum computers shown as the orange circle at the bottom middle. And on the left, we have a cartoon of a quantum switch, which can route quantum signals between different locations. Now, we also have a quantum repeater, and I've circled this one in green because I like to identify that as a major challenge and one of the goals of the CQN's research programs. So what a quantum repeater does is the following. If if you're trying to send quantum information from one of those red nodes to another red node over, say, a few thousand kilometers, that's very hard to do using optical fibers, because although fibers are very good, after a few hundred kilometers, the photons that are traveling inside the fiber actually leak out and they're lost forever. And so that's not good, right? So in an ordinary internet, you have something called a repeater. What it does is it intercepts the signal before the signal is too weak. It amplifies it and sends it on its way. By amplification, I mean, like on your stereo, you have the volume knob. You turn up the volume, and you can convert a weak signal into a strong signal. And we have the same thing for optical internet repeaters. That only works for classical light. It doesn't work for quantum signals. And I'll describe more why that is later. But the problem is that when you try to amplify a quantum signal, you disturb it, you change it, and the information is no longer correct. So this is a problem. How do we do this? There are ways known theoretically how to do this, but actually building these devices is very difficult. So with that overview, I want to go through as much as I can this beginner's introduction to the underlying physics. So I never miss a chance to plug my little paperback book shown here. And this is a easy to read book. I've handed it to congresspersons and CEOs of various companies and so on. People say they like it. Also, I use this book in a course that I teach sometimes at the university here and elsewhere. And we have some YouTube lectures coming that were prepared jointly with Harvard University and Howard University last summer, and we'll be notifying people when those lectures are available. Okay, now to the real physics here. What is a quantum state? So, I've talked about things like quantum state, entanglement, superposition, and so on. Well, what is a state? A state is a description of the state of an object or a system. And the example I like to use is the president's State of the Union. That's where he or she describes the condition of the country. Okay, so quantum state describes the condition or the state of a quantum object. We use the symbol psi, but we also like to use a bracket notation. And the brackets are shown here. What's inside the bracket is a little picture of the object, and the green circles indicate the state of the object. So here's, for example, an electron. It could either be spinning clockwise or counterclockwise with respect to the vertical direction. Those are two possible states. Okay. Now, if we take that same electron and we look at it from a different point of view, we can ask, is that electron spinning clockwise or counterclockwise with respect to a horizontal direction? And what the quantum mathematics allows us to do is to answer a question like the following. Let's say you know that the quantum state is clockwise around the vertical because you prepared it that way using a laser or something. Now you take that same particle or electron and you measure it in a horizontal direction. You ask the question using some apparatus, is it spinning clockwise or counterclockwise around a horizontal direction? These are three-dimensional objects, so they can have different orientations of their spin or different axes of their spin. It turns out if you make that measurement, you have 50% probability to get clockwise or horizontal, or clockwise, or counterclockwise horizontal. And if you repeat this same experiment many times, half the time you get clockwise and half the time you get counterclockwise. And this is a strong indication that there's something probabilistic. There's something you might call it random. But certainly, in order to describe the situation, you have to use probability theory and statistics. And this is intrinsic to quantum physics. It's not the same as flipping a coin. Coin flip is random, but if you knew exactly how your thumb were accelerating the coin, and you could calculate that perfectly using classical physics, you could predict exactly how the coin will land. In fact, I think a robotic coin flipper can flip heads every time. But with quantum mechanics, that's not the case. There's no underlying trajectory or mechanism that determines clockwise or counterclockwise. It's intrinsically random as far as we know, and that's just the way nature is, as far as we know. Another important point, the particle was initially prepared spinning clockwise in the vertical axis, but after we've measured it in a horizontal axis, the electron forgets its earlier state. It's been reset into a new state. And this forgetting of the state that it used to be in lies at the heart of quantum cryptography. Namely, we can use these binary choices of states, clockwise or counterclockwise, to encode some information, and that could be forming a cryptographic key, which would be used later for encryption and decryption. But now if an eavesdropper comes along and intercepts one of those particles and measures the state, then the original state is forgotten, it's disturbed. And this very disturbance is related to what they call Heisenberg's uncertainty principle. And this disturbance allows the legitimate users of the cryptographic key to detect the presence of the eavesdropper and to take the appropriate action to somehow get around that. Okay. Now let's talk about superposition, not superstition, superposition and entanglement. Well, here's a superstition, I guess, which is really a superposition of a single object indicated here as a cat. And this cat could be in one of two states. And the usual humorous cartoon is a dead cat and an alive cat. Now the plus sign, it doesn't mean there's two cats. It doesn't mean there's one cat dead and one cat alive. I mean, there's only one cat here, but the cat is simultaneously has the possibilities to be alive or dead if you were to make the observation or the measurement. Now, it's not true that the cat is simultaneously dead and alive. That's sort of a nonsensical thing. What it really means is that if the cat is prepared in this way, and it's really not a cat, it's really an electron with two possible states. If it's prepared in this way, in the superposition way, and then you measure it, you'll get one or the other with a 50% probability. But again, that doesn't mean that there's a mechanism. It's not like flipping a coin and getting one or the other. It's really that two possibilities are simultaneously held within the intrinsic nature of this object. And when you measure it, there's a apparently random decision or choice that's made by the universe, and it reveals one of these results or the other result. That's called quantum superposition. Now, next important concept is the composite state. If I have two objects, a cat and a bottle, well, I can represent the combined or composite condition or state of the two objects together in this way with an ampersand between them. So I have to specify both the properties of both of these. Well, here's an example of entanglement. I have shown here two possible states of the composite object. On the left is the cat alive and the bottle sealed. And on the right is the state in which the cat is dead and the bottle has been broken. The usual story is maybe there's poison inside the bottle, which kills the cat. Okay. Of course, in reality, these quantum states don't apply to large objects like cats and bottles. This is just a representation. It only really applies to electrons and photons. Okay, but the point is that now we have a correlation, because if I go in and measure the property of the bottle, let's say I measure the bottle and I don't measure the cat. Well, if I see the bottle unbroken, then I can infer without actually looking at the cat that the cat must be alive if I measure that cat. But if I see the bottle broken, I can infer that the cat, if I look at the cat, will be dead. Now, notice I use the word infer. That's very important. It's not that when I looked at it, I caused the cat to be alive or dead. It's that when I gain information about the state of the bottle, I can use that new information to infer or to make a prediction about what I will see if I look at the cat. That's information. I've gained information when I looked at the bottle. I didn't physically cause anything to happen by looking at the bottle. Okay. Now, the concept of non-local quantum correlation is very important. So here again, I show the example of the entangled state, the two possible composite states with a plus sign between them, indicating that there's superposition between these two composite states. And this is what we call entanglement. Fine. But now here's a very interesting fact. I can move the bottle to the right as far as I want. After I make this state, however I make it, I can move the bottle very far away to the right or a large distance. It can be arbitrarily large distance. And this superposition of composite states still remains an entangled state. So now the bottle could be many kilometers away from the cat, and I could look at the bottle and see if it's broken or not. And I can infer then what state the cat will be if somebody else looks at the cat many kilometers away. Okay, so this is called a non-local correlation. Now, some kind of correlations like this also exist in classical physics, but not of this quantum nature. There's a very big difference between those two, but I don't have time right now to go into the details of exactly what that difference is. But you can prove very rigorously that there's a difference between these long distance quantum correlations and long distance classical correlations. And again, correlation does not imply causation. If I look at the bottle and I see it's broken, that does not cause the cat to die or not die. There's no physical back action or action at a distance between these two sides. It's simply that when I look at the bottle, I gain information and I can infer something about the state of the cat. Notice I can infer that instantaneously, but that doesn't break the speed of light because there's no physical influence traveling from the bottle to the cat. It's just that I know something about the cat that other people don't know. Okay, another key principle in quantum physics is called the no cloning theorem. And I'm going to skip through this because time is running short. And the idea is you cannot copy a quantum state without destroying it. And the other point is you cannot determine the state of a single quantum object by making measurements on that single object. And let me skip over that. Let's talk about about communication networks, since that's why we're here. Okay, what is a network? It's a network of channels that transmits or shares information between nodes. So in this cartoon, the balls are the nodes and the lines are the channels. And in a classical network, I can write a message on a pad, a notebook, hi there, and I can send that information digitally into the network, and it comes out the other end and appears on a screen, hi there. Okay, but the points about classical information are the following. This information can be represented by the classical states of objects, such as symbols on a paper, or marks, or symbols on a screen. You can copy this information as many times as you want with a copy machine without destroying the original. And as I said on the previous slide, that's not possible with quantum information, because when you try to copy it, you disturb it actually. Okay. Notice that we don't send the tablet, we send the information that was on the tablet. Great. Now, what is a quantum communication network? Well, again, it's a network of channels, but it has to send quantum information. So you might ask, what is quantum information? Well, I've hinted around at this, but formally, it is information encoded in entangled quantum states of physical objects. Okay, so here we have, for example, on the lower left, we have the quantum state of a spinning electron. In its particular state, it may be entangled with some other nearby electrons. We want to send the information about that state through the network and arrive at the other side. But notice, we don't want to send the actual electron. We don't send the electron. We keep the electron back on the left. We just have to transmit the information about the state over to some electron on the right. We don't send the object. Okay, this kind of information cannot be represented by symbols on paper or symbols on a computer screen. It has to be represented by the quantum states of elementary objects, such as electrons or photons. And when it travels through the network, it's not supposed to leave any trace. Namely, it's not supposed to interact permanently with any parts of the network, because if it did, that would disturb the quantum state. And we don't want that. We want that state to go through transparently. And only under that conditions can we maintain entanglement. So if the electron on the left is entangled with some other electron, and then we transmit that information to the electron on the right, we want that electron on the right to be entangled with the other one on the left. And this only happens if there's no permanent disturbance or trace left in the network. Okay, so we want to send a quantum state without sending the object. All right, now how do we do this? I'm going to go through some slides fairly quickly because I've gone too slow already. But I want to sketch out how quantum state teleportation can work. So first we have to do entanglement swapping. So down here we have a source that produces two particles, A and B, and those are in some entangled state. That's like the cat and the bottle. On the right, we have another source that produces a different entangled pair, like the cat and a bottle, different pair. What we do is we take the B particle from here and the C particle from here. Let's say we take the two bottles and we put them into a measurement that produces a measurement not of each individual bottle, but of some joint property of the two bottles. We get some outcome. So for example, it could be if both bottles are broken, we get a 1. If both bottles are not broken, we get a 0, so something like that. Okay, and then we take that outcome and we transform it. We simply send that outcome. That's like a classical piece of information. And if we know that information, this tells us now that the particles A and D are now entangled. And this is interesting because those particles never came into physical contact with each other. Only B and C did. But now we've finally produced A and D in an entangled state. Again, it means our information about A and D are somehow entangled because we had initial correlations between A and B and correlations between C and D. We made a measurement on B and C, which then entangled our information about A and D. So it's not that the particles are entangled, really. It's our knowledge of the particles are entangled. Okay, so teleportation uses entanglement in the following way. Let's say Professor Xavier here has a particle called X, and he wants to put that into a quantum state psi, which he does, and then he wants to transmit that quantum state over to Bob, but does not want to send the particle X over to Bob. How can he teleport the information about that particle over to Bob? Here's how they do it. They take one of these entangled state resources, which produces two particles, A and B, which are in some entangled state. Great, they send one to Bob and one to Alice. This is a resource, I'll talk about that later. So now the particle A goes into a joint measurement device with the particle X. The outcome is known by Alice. She looks at that, she records it on a piece of paper. She calls Bob up on a telephone, tells Bob the answer was 0 or the answer was 1. And then what Bob does is he uses that information to perform a very simple operation called unitary operation, some kind of a transformation on this particle, which is a very simple thing to do. And then this particle B magically turns into the particle, the state psi, which was the same state that Professor Xavier produced this particle X to be in initially. Now notice the state of particle A and the state of particle X are now destroyed because they forget their state, as I said earlier. And so we haven't copied or cloned the state of psi. We've simply transferred it across space over to this other particle. And this distance here can be arbitrarily large. It could be hundreds of kilometers, thousands of kilometers. Now notice that Alice never knew the state psi. She just made the measurement and called up Bob and told him what the result was. Notice also this process is not instantaneous. That's because when Bob gets the result from Alice, he has to wait for a certain amount of time for the phone call to transmit the information to him, so he knows what transformation to do on this particle to produce the state psi. So it's not instantaneous. Quantum communication is always limited by the speed of light, just like classical communication. All right. It also works if this particle X is entangled with the particle Y, and then we teleport the state of X over to this particle B. Now the particle B is entangled with the particle Y. So this is how we can send in different stages. We can distribute entanglement farther and farther, because now we could take the state of this Y, of this particle B, and we could teleport it to another location. And we can kind of daisy chain our way out to larger and larger distances. Okay. And I'll skip this slide. It just says if we have quantum memories, we can make this whole process more efficient. Okay. Now, NASA is working on building a project now to put a satellite in Earth orbit and do some of these teleportation and entanglement distribution operations from space down to these ground stations or telescopes, which can receive the photons. Okay. I'll skip over this quickly. Entanglement in space has many technical applications. You can use it to build a long distance quantum internet. Remember, I mentioned that optical fibers are problematic because the photons get lost out the sides. Well, with a satellite, there's sort of like nothing in between the satellite and the ground, so that photon doesn't really get lost. It might spread out over a large area. That's why you need a large telescope to collect it. But there's nothing in the way that would make it actually get lost. So in the early days, over the next 5 or 10 years, we think that satellite networks might outperform fiber networks for long distance communication. But in 20 years, maybe the optical fiber schemes will catch up, as long as you can build a quantum repeater, which I said was difficult. So this is just an example of the project. The US is building a project called Marconi 2.0, where the satellite will try to generate entanglement and teleportation across different continents, ideally. And with the memories, you can enhance this. So this second to last slide is a little modified document that I created, which makes the point that entanglement is a resource. And the purpose of a quantum network is to distribute that resource to different locations. So I made up this company called the Southern Entanglement Provider, and this is your entanglement account, and this is your monthly bill. And down here it shows that there's the E-meter, that's the entanglement meter. It records how many entangled quantum objects, most likely photons, you received during that month. And then E-bits is the same measurement, entanglement bits. And then these are your surcharges, a certain amount of money per entanglement bit. And I make this point because we're used to having a utility that distributes energy in the form of electricity, usually, and we pay for that. A certain amount of kilowatt hours, you pay money for that. Well, in the future, entanglement will be a similar resource that one has to pay for, or you could get it free if you want to. But the point is, it's a measurable, a quantifiable, valuable commodity that has to be transmitted from one location to another. Actually, first it has to be created and then transferred. Okay, so in summary, I want to just remind everybody how quantum networks are different from classical networks. First of all, information is stored and transmitted in the form of the states of quantum entities. It cannot be written down on paper. Secondly, quantum information cannot be copied without destroying the original. That's very different than classical information. quantum information can be teleported using entanglement. And again, we do not teleport the object, we only teleport the information about the object. But it can be the full quantum information that we teleport, which is not, this teleportation is not instantaneous, of course. It's an entanglement is a resource that can be provided to users through a quantum network. And that is the goal of our project, is to learn how to build such networks that can actually distribute these entangled objects. Well, I should say entangled states, not entangled objects. So a big goal is to build a quantum repeater and also fault tolerant memories, which I didn't talk about very much, but you need to be able to store quantum information in a computer memory, which will consist of single atoms, millions of single atoms, each one storing a single quantum bit, and so on. And this is a very big, important goal. And there's a lot of competition worldwide to try to build the first practical quantum repeaters. And finally, because we like optics and photonics, we like to advertise the fact that almost all quantum technologies do use optics and photonics, which means lasers, detectors, optical fibers, and so on, to build quantum technologies. So with that, I will end and be happy to take questions. Thank you.
All right, thank you. Yep, so if anybody has any questions, go ahead and you can unmute yourself and ask away.
Hi, can I ask a quick question?
Yes.
So if it's possible, can you also give an example of the AI and machine learning impact, the impact that a quantum network will have on AI and machine learning, actually quantum computing, if I got my lessons right.
Yes. The question is, how can quantum computers be used to advance artificial intelligence and machine learning, which are, in some sense, one and the same thing. I'm no expert on this. So let me just say it this way, that we really don't know for certain right now which kind of applications quantum computers will be most useful for. And I should emphasize also that most applications and many applications will not be enhanced by using quantum computers. There are only certain kind of problems that can be enhanced. And those are the ones that can be mapped one-to-one onto a quantum mechanical calculation. So the challenge is in, say, for example, in machine learning is, there what you do is you have a bunch of objects, test objects, you train your computer algorithm on these test objects, maybe millions or even billions of test objects, and then you feed it a new or novel object, and you say, well, which of those test objects is your novel object most similar to? So this is kind of a search and correlation activity, and the classical computer would have to search through all these millions of test objects almost like sequentially and match them up with some kind of a network to speed things up. But a quantum computer, because it works with superposition and entanglement, can, in some sense, probe that whole space of test objects simultaneously and whittle down or narrow down the closest matches much more efficiently than could a classical computer. So we won't have quantum AI for another 15, 20 years probably, because it requires very large overhead and nearly ideal quantum computers. So at this point, it's really more of a research topic.
Thank you.
I do see one question from Mark Ringsletter, who asked, couldn't you also look at the dead cat and infer that the bottle must be broken and contain poison? And the answer is yes. For some reason, I always chose to say, look at the bottle first, because that seems more causal, right? But it's actually a better example to look at the cat. And then if you see the cat is dead, that didn't cause the bottle to be broken. It just is correlated with the fact that the bottle is broken. So that's a good point. Any other questions? I'm very happy to entertain.
Can I ask one more question?
Any kind of question. Okay.
So this is just a more general one. I'm a lawyer, not a scientist, so please forgive my ignorance. So when you went to Congress, I'm just wondering, how do you persuade people who, I mean, when we're talking about, for example, that this technology will not be around maybe for more than 15 years or 10 years, do we know for sure that we're going to get there, but it's just a matter of time? Or is it also a hope that something like this will exist? I mean, I'm just wondering, how do we persuade legislature that this is something that we can do, rather than this is something that we can hope we can do, even if it takes a long time? I mean, generally in science speaking.
Yes. Yes, yeah, that was exactly the challenge that we and other people have and still have with lobbying policymakers to support this. So the way we try to present it was with sort of two sides of it. One is, right now we're at the same stage as the semiconductor revolution was around 1960. And at that time, we barely had a very rudimentary microprocessor. And so we say, look, there's an example where we didn't know what the ultimate consequences of semiconductors would be: computers, internet, cell phones, and so on. But they were enormous. And the science and engineering community has now spent about 30 or 40 years studying this quantum information idea, and have now come to the consensus that it is doable, it will work, it will produce something. But just like they couldn't predict in 1960 what computers would produce, we cannot predict exactly what quantum technology will produce. That's the first answer. Well, the second answer is there's great competition and there's great economic impact in this space. So it's certainly a job creator, and it will produce something. Just can't say what. And then I should add a third one, which is very important, and that is scientific progress. The scientific community is really convinced very strongly that by studying quantum information science and trying to build the corresponding technology, we will be able to learn new facts about science, about the nature of the universe, in really dramatically different ways than we could without that. So those are three answers. I see a question from Laura Denotis.
Hi, Michael. I was really struck by your statement about, if I'm saying this right, the quantum information not being able to interact with anything that disturbs it from point A to point B. And when you think about all of the in medias res interventions in a network right now, whether to do with security or error checking or deep packet, and whatever the quantum equivalent of those things would be, what kind of constraints does that create, and does it imply a radical decentralization, or can you say anything about that?
It's true that if an eavesdropper or if a legitimate player wants to monitor the information flowing on the quantum network, this has to be designed in a way that they cannot actually learn what the information is that they're monitoring. They might be able to say a quantum packet went from A to B successfully, and the node should report that. But nobody except the legitimate users at the end nodes would be allowed to know what that information is. If they did, it would simply break the information. So in a way, that's what provides security, but it also means the government cannot have any backdoors on this information, because they will be detected and they will break the communication itself. So this is a real game changer if it does take place. It also requires an extremely different kind of technology than we have now.
Thank you.
There are a couple of more questions in the chat. I'll just take a look here. there's a funny joke about dogs versus cats in the chat window. The speculation is that the dogs must have set up the scientists to always use the cats as the example. It was actually Erwin Schrödinger back in around 1927 or so who first came up with this cat example. But we don't know if he was a dog lover. Another question is from Katie Schwartz. Says, you mentioned how quantum information has to be created and then sent. Is there an energy consumption and footprint difference between quantum and classical computing? I saw just today, browsing through the online news, that there's a study, which I didn't look at, but it said that the energy consumption of quantum computer can be far less than energy consumption of classical computer. And it's kind of hard to explain why that is, but a simple answer is that, well, you're dealing with single electrons and single atoms. They're very small. Each one uses or contains very, very small amount of energy. But what's not clear to me, whether that statement is true, is that even though the quantum bit contains very little energy, to actually run the machine, the lasers, the ion traps, the superconductors and all that, that still takes a lot of classical infrastructure. And so I think people are starting to look at, as you miniaturize these quantum computing devices, how the energy consumption scales. And I believe, although I haven't studied it, I think people are proposing that a quantum computer could be built that consumes a lot less energy or power than a classical computer. But I'm no expert on that. I don't know.
All right, we're a little bit past here. Does anybody have any last questions? Speak now or forever hold your peace.
So when the message goes, real quick, sorry. When the message goes out, the end user knows what they're supposed to have, right? Is there any way that message could get intercepted in the middle? I understand that the message through the quantum state is pretty secure, but what's to say that message that goes from the beginner to the end, can that be compromised in any way?
I think what you're saying is we're asking is when the message or the quantum data is received at the end by the legitimate user, then how is that handled and is it secure? And I think there's two answers. One is the fact that there's always human error, and you can always threaten a person and say, give me your quantum data or I'm going to harm you. So there's always that factor. But assuming that that's not the case, then it depends on what that recipient uses that information for. For example, that recipient could take that quantum information and feed it into a locally held quantum processor or computer, process that information and send it back to the original sender. And the person who received it and processed it and sent it back would never know what that information consisted of. If they knew that, it would break the calculation.
Okay.
So they're not allowed to know that. But if they just want to use it for their own purposes, like store it locally in a quantum memory, then they can store it there. But again, the only way they can access that information is with a quantum readout device. And when they actually read out that information, they will make that information classical because they'll write that down on a piece of paper, and it will erase the quantum information in their locally held memory.
Okay, I get the key to the end piece is in your slide, the classical information between Alice and Bob, right? That's the piece that, could that piece be intercepted? Because the other pieces sounds like it's going to be pretty secure.
Well, the information in between, if I understand, it could certainly be intercepted by an eavesdropper, but then Alice and Bob at the two ends would be able to check and know that this information was intercepted, and they could have a strategy to get around that. And a more detailed answer is that there are ways to embed the information in larger sets of data, small amount of information in a large set of data. This is called error correction. And you can code the information in ways that if the eavesdropper intercepts a small amount of information, you can kind of cover that up and correct for it and squeeze out the eavesdropper so they still don't get any useful information. And Alice and Bob can still exchange useful amounts of quantum information.
Okay.
But this requires lots of overhead, lots of quantum processors and error correction, which we don't have right now.
Okay. Thank you for your time today, Doctor.
Thank you.
All right. Well, I think that's probably a good time to stop. Just wanted to let everybody know that we are hoping that this will become a regular occurrence, a monthly event. So just to let everybody know, Dr. Guha is scheduled to talk next month on May 21st. Still trying to figure out the title and the topic for that, but we will send out information about that pretty soon here. So that will be going on. And then also we're going to be sending out a survey. It'd be great if people can fill that out. Just it helps us understand what kind of topics and speakers that you would like to see in the future. And I want to thank Dr. Raymer, of course, for giving us our first talk in this series and for everybody for attending. So everybody enjoy your weekend.